All right, welcome again. Again, thank you, Carson, for being our presenter tonight. Carson has been a regular for a few years now, I think many years. And we've all gleaned from your desire and also your ability to present on hard things and interesting things. And so we appreciate your willingness to do it. If you have other speakers or topics, please let me know. For those who are not in the Forge Slack, please join. I can put that link again, but there's a lot of good conversation that happens there, but also suggestions of other topics. So thank you, Carson. Again, we'll just go as so long as you want, and then we'll have other discussions as always.
That's a dangerous open-ended presentation. This will be medium-sized lunch. Thanks, Paul. So, in case you didn't catch it, my name again is Carson Anderson. I call myself the DevXO at Weave. The DevX team is the developer experience team at Weave, and I consider myself the executive officer. It's a made-up title, but aren't they all? So, I'm the DevXO at Weave. We build a lot of the tooling and help our developers run the product at Weave without having to dig too much into the weeds. And I am also really excited to talk about a bunch of ways to do mTLS and Kubernetes, because I'm sick of hearing that there's only one way to do it and that the only answer is a service mesh. That's how you get mTLS, because that's what service meshes do. Like, no, we can do it, and we can do it 5 different ways. And somebody asked coming in today, how many of these have you actually used? And my answer is all of them. We're going to use all of them today here. So there's a lot of demos, there's a lot of code. It's a very, very code heavy. Tell me if something doesn't make sense, or if I've got a snippet of code that you don't understand the context of. I really want to dive into not the mechanisms, how these work, and kind of build up from the bottom level up to something more automated. And what do I mean by that? We're going to do 5 different ways of mTLS and Kubernetes, and I'm sort of cheating here, but not really, because the flavor 0, if you will, is not, right? One way to do mTLS anywhere, including Kubernetes, is to not do it. Arguably, the most popular way to do mTLS is to not do it. So this is going to give us a really nice foundation of how, what we're trying to solve, right? We're going to start with the base level, just put a thing in there, and then start adding mTLS on in multiple stages and kind of building more and more, pushing more and more of our TLS infrastructure into the cluster or other tools, and kind of understanding where we get. So we're going to go no mTLS at all. Then we're going to do everything by hand, including putting in Kubernetes by hand. Then we're going to use Cert Manager to do it kind of by hand, and you'll see the difference between 2 and 3 when we get there. Then we're going to do number 3, which is my favorite. This is kind of the entire reason I wanted to do this, so I could play with number 3, which is where I'm using Cert Manager to distribute certs, but it does it completely for me, which is really cool, and CSI is really, really neat, and we'll get there. And then last, we're going to do mTLS with a service mesh, because that's the way everybody thinks is the only way you can do it. And I'm going to do that last because what you see, like, yes, it does a bunch of things. Yes, it makes things easier, but you lose something. There's a trade-off there. So we'll talk about that when we get there. Flavor 0, we're going to start here. We're going to not do mTLS. And before we do that, I went back and forth about what we're going to deploy as a sample of like doing mTLS. Right? We could deploy a web server and have client auth. We could do any sort of application that supported mTLS, but I like Go, and Kubernetes is written in Go, and Cloud Native does Go. So it's actually really easy to just write our own HTTP server and client in Go that does both not mTLS and mTLS. So we're going to write 2 of these today to kind of give a foundation of, it doesn't have to be a whole program. Like, it's actually, in modern languages, pretty easy to use these and set these up in your applications themselves. So very, very basic code. If you haven't seen something like this, I would be shocked. This is the bare bones basic HTTP server in Go code, right? So we're going to listen on port 8080. Every single request that comes in, we don't care about your path or your method or any of that. Every single request is going to just print out the request headers to the console of the server, respond to the client with hello, and we're done, right? So that's all this is setting up the server and starting it. It's really, really boring. You've probably seen this a million times, but we're going to make this more advanced when we get to the TLS part. Our client code is a bit longer, but basically the bare bones Go client. You tell me what the URL is you want to hit. We're going to set up a client with a timeout. We're going to print that we're starting a request loop. And every second, we're going to try to get from that URL. And if we do, we're going to read the body and then we're going to print from the client to the client's terminal the response headers we got back from the server and the response body, right? So the server's going to print out the headers it got from the client's going to say, here's what I got back and here's the body. Very, very bare bones code. Again, we're going to extend this as we start doing mTLS, and this will kind of help us understand the components we're working with. So just to prove this works, we got a demo to run the server. I'm calling it the insecure server because it is just HTTP. Going to wait a little while for it to come up and then start the client on that server's listen port. So don't worry about the kill. That's to kill things I've left around in previous runs. There we go. So we started the server, we started the client, and you can see the server says, hey, here's the request headers coming in from the client, and the client says, here's the request or the response headers from the server and the body, right? Not interesting, but just to prove it all does work. And you're going to see this a lot as we test mTLS in all the different ways. You're going to see this kind of request response in our logs over and over again. So get used to it. So what just happened? Again, not interesting. I'm building on this, I promise. The client started a connection to an HTTP server. The server accepted the client connection. The client sent its payload. The server sent the response. This is not a surprise, but I want to put some emphasis in here and add some words because this changes the context of why we care about mTLS. The client started a connection to any HTTP server. The server accepted the connection from any client, and then the client sent the payload. In this graph, there are no guarantees anywhere, right? There's no guarantee that who I'm talking to is who I think I'm talking to, and if I'm the server, there's no guarantee that who's coming in is who I think it's coming in. I can't verify identity either way. Not to mention that that communication is all completely clear text, so it's unencrypted, so anybody in the middle could read that traffic if not modify it. That's important because our basic server opens this up to things like this, right? Somebody could maliciously or on purpose, or not maliciously, whatever, could stick a proxy between my client and my server, and neither would know, especially if the proxy is just reading data and forwarding it on, or maybe reading data and tweaking some values about your payloads or whatever. You could have a transparent proxy in there sniffing all your traffic and you wouldn't even know. Think you'd know, but if it's getting your connection back and forth, it could just be right in the middle, doing whatever it wants, slurping up all your headers, right? Because once we've connected, we don't care who you are. Here's the payload, including all my auth headers, the body, everything. You could also do something like this, where when the client says, well, I need to talk to localhost, it goes out to, localhost wouldn't go to DNS, but I need to talk to a specific server address. It goes out and maybe you've got poison DNS. And so the client makes a connection to some other server that is looking and serving the same kind of API you expect, but maybe slurping all your data up, right? You just have no guarantees. In this case, the server that we wrote is out in this other box, completely being ignored and unused. And we want to prevent from that, right? We want to know as a client, we're talking to who we expect. And the server, ideally in an mTLS scenario, wants to know, yes, this is a client. And I don't have an example of a fake client, but you can see there's no guarantees anywhere, right? So we solved this with TLS. We solved part of this with TLS, and then we solved the other part with mTLS. And we'll get there, right? I need to basically make some assurances in this loop that when I talk to the server, I really am talking to the server, and when it knows that it's really me. So in order to do that, let's, before we get into that though, we're gonna deploy our code. So I kind of jumped ahead. We're gonna actually deploy our mTLS into Kubernetes, because I'm gonna build on this. So we take our insecure server, and I'm basically building a stock Kubernetes deployment here. There's nothing interesting about this. This is like the basic Kubernetes deployment resource that you've seen a million times. If you don't know what this is, you throw this at the cluster. The cluster then ensures you have a set number of replicas matching a specification. And the important part here is that we are telling, in this deployment, zooming in on the container section, we're saying, run my Go test app image, and I want you to call the server and run that as the entry point for that container, right? So I'm going to have a copy of my server running in the cluster. Then we're going to make a Kubernetes service that says, okay, we have a service called server that is going to point to all of the pods that have the selector app test server, which was part of our previous deployment spec up here, right? Very, very bare bones. Here's the deployment. Here's the Kubernetes service pointing at the deployment. Then we're going to make a client deployment, which is almost identical to our server deployment. Again, just saying run one copy of our server and a couple copies of our client. The only real difference here is that we're calling the client in the arguments and giving it the path of the server. In this case, it's not localhost, it's the fully qualified DNS name of the service that we made for our server, right? So it's going to go look up in DNS server default.service.cluster.local. Go there. And if you've done all this, I promise it gets a lot more interesting as we get into the mTLS stuff, but I want to set a good foundation. One thing we're going to do 5 times today is this. We're going to run a Kubernetes cluster. I'm going to use K3D because I like using K3D for demos because I can make them really, really quickly. So we're going to run this command K3D cluster create to create a cluster called 0-none. Then, because I don't want to use Docker Hub or a registry, I'm going to build my Go test app locally, save that as a tar file, and then use K3D to basically take that image and jam it into all the nodes for the Docker cluster, right? So I'm making a local cluster in a Docker container and using K3D to say, take these images and stick them on those nodes so you don't have to download them. That allows me to screw with my code all I want and not have to push images. I just have to rerun these commands, including the cluster is going to be empty. It's going to have no images, including my private ones. So this is how I get that there. Then we're going to apply the server YAML and the client YAML. I'm going to wait for them to come up and watch the logs. This is just to say, don't colorize this output because GoPresent does not like colorized output. So let's go ahead and do it. You're going to see this a lot. I'm not going to show you the cluster setup steps. They're going to be the same. I'm always going to make a new cluster and stick the Docker image in there. So you'll see these logs even if you don't see it on subsequent demos. So this is K3D saying, yep, let me bring up this cluster called 0-none, initialize it, set up your kubectl so that it by default points to this new cluster that I just made. So that's how all my kubectl commands in the script go to the right clusters. It's just set up by default by K3D. Here's me building my image, which is going to be really fast because the code hasn't changed. So I built the image, exports it to a tar, and sticks that in the cluster. I also have to say, I don't wait for the metrics service in the K3D cluster to come up. So some kubeconfig or kubectl commands will spew this memcache error. Just let your eyes glaze over it. It doesn't matter. And if you can't read it, I'll kind of just what's going on here as well. So this is now we're down to the kubectl apply server YAML, which creates the server deployment and service and the client deployment. Then we wait for them to come up and then lower down. Here we go. Here's our logs starting, and this should look pretty much identical to the logs that we were seeing before, right? When we were running this code locally, we were seeing request headers go out and response headers come back and the response body. And it's just going to loop over this. And in this case, we have a couple different client pods that are hitting the server, right? And that's going to be important later that we have 2 different client pods that are technically 2 unique instances of our code that we'll want to identify later. But right now, it's all completely unencrypted, right? We had our server talk to the client, and the client talk to the server, and we hope they go to the right place. We're trusting Kubernetes to get things to the right place, but there are no guarantees. Our code has no promises, and we don't know for sure where we're going. So this is what happened. This is very similar to our previous poison DNS example. Nothing's poisoned here, but you see how immediately in our first Kubernetes deploy, because of all this indirection of Kubernetes, if somebody gets access to the Kubernetes API or can tweak our service, it could easily not even poison the DNS, just straight up change our service definition in Kubernetes to point to a different set of pods. That may be an administrator doing that for important reasons. It may be malicious, but you're still trusting. Like you're in Kubernetes, we kind of trust that things are going to be good, but you're still really trusting DNS here. Like we immediately come into this case where without any sort of TLS or mTLS, there's no promises anywhere. Other than that, it's the same as before with our client and server, other than we go through this load balancer that's discovered through the DNS. So we want to solve this, right? We want to know that as a client, when I talk to the server, I am talking to that server, right? And if I am, for example, on my web browser going to google.com or amazon.com, I want to know that I'm really going there because I don't want to send my credit card information to a fake amazon.com, right? And so that's sort of the TLS that we're used to dealing with. We're used to dealing with single directional TLS, not mutual, but just I go to amazon.com and I can trust that they present to me a certificate and therefore I know that that's really amazon.com. Amazon really has no built-in guarantees at the protocol level that I'm me. That's what logging in is for, but there are ways that they could use actual certificates both ways to do a deeper verification. And we'll get into that. So like I said, we want to start making promises. We want to know who we're talking to and be able to guarantee that at the root level, and then also encrypt this traffic so no one can sniff it along the way. So let's change our code to support mTLS. First thing we're going to need to do is in our server, we're going to need to start taking some arguments. The crux of all mTLS and TLS is how do you get certs to things? 99% of what we're going to work on today is well, it's 50% is generating certs, and the other 50% is how do we get those certs to the code, right? So, but the code either way needs to take some parameters to say, where do these things live? So we're going to make sure that we have a cert file and a key file, which is essentially, you tell me who you are, and here's how you prove it. And then a CA, meaning another authority that I'm going to trust. And I'll kind of dig into why we have an extra CA in a second. But these are three really common things you'll see when you're doing mTLS. And once we've taken those arguments, those are just paths to files. We're going to then in our code, we're going to initialize a CA cert pool. This is how Go does it. Again, if you're using some other mTLS, if you're just building mTLS on like Nginx or whatever, you put in there config those values and you're done. But I'm showing you how we do this in Go. So I'm going to build a cert pool saying take all the root certificates off of my system and trust them. We'll get into what root certs are in case you don't know, but take all the roots that are on my system and trust them. Read a cert out of this file, and I want you to add them into the pool of trust. So not only do I trust all of the authorities that are on my system, I'm going to trust an extra one. And like I said, if you don't know what root CAs are, when I go to Amazon.com, they present to me a cert that is signed with their key, so I know that it really came from them, and they own that cert. And typically, I don't really trust that cert directly, right? It says, well, I came from this other CA, and that cert came from this other cert, and that cert came from this other cert, as far down as we need to go till I get to some root authority. And if you don't know this, on every computer you've ever had, somewhere in the file system, there's a big bunch of files that are your root certificates, right? They're just literally just certificate files from the root authorities that get installed and distributed with your operating system. And that's how things like your web browser by default can verify that you're really talking to, even not trust Amazon directly, but you'll trust somebody who trusts somebody who trusts somebody who trusts Amazon. And that chain is really involved a lot in your normal day-to-day, like HTTPS in your web browser. But when we're doing mTLS ourselves, we typically don't want to have to pay somebody to get a certificate at the end of that trusted chain, right? You typically have to pay DigiCert, or now there's Let's Encrypt, but even that has limitations on speed and what you can issue. So we're going to make our own CA, and we're going to pass it in and say, trust all those and our CA. You don't have to trust all the roots here, but I like to do it as just a standard practice. Then we take our cert file and key file arguments and build a certificate. We're going to then build a TLS configuration for the server that says, when people try to connect to you, send them this cert. And before you finish the connection with them, I'll use these extra CAs to verify their certificate, right? So here's the mTLS part. This top part is really, really common if you're in Go and just want to serve your server with TLS. You just say, here's the certificate you're going to use when you serve. But the client part's the tricky part, because you have to add these extra arguments to do the mutual part, which says not only are you going to use a cert to verify, you're going to ask them to use a cert to verify before you do anything. Which is the mutual part of mTLS. Then finally, once we build our cert pool, we built our certificate, create the config. We're going to create a server that listens on a new port, just as a common standard. We're going to inject that config. We're going to set up our handler again. The handler's gotten a little fancier. We're still not routing. We don't care about path. We don't care about method, any of that. But we're going to do something really cool with this cert data that our client's giving us. And we're going to use the TLS struct in the request to actually dig in and say, while I'm handling this request, I know the client had to provide a cert. Let me get info out of that certificate and use it as part of my request. I don't have to do this. It would have still done mTLS even if my route didn't use that data, but it's really cool that this data is here. And you'll see as we get further and further, these responses, when I print back to the console, the client names, they're going to get more and more specific as we use different mTLS providers. So we can actually use this data to identify clients as uniquely as we want to basically generate certificates. So we're going to print out your names, we're going to print your headers, and we're going to use the names in the response to say, hey, hello, all your names. Thank you for using mTLS. And finally, we're going to start the server with TLS. The client code is really, really similar. Again, we're going to take who are you, how do you prove it, and who else are you going to trust? And then also for the client, who are you going to hit when you do your requests. This is the same code as before. Build a cert pool, add our additional trust in here, build a certificate, and then when we make our client, we're going to use this transport config and a TLS client config to say, here's the root CAs that we want you to use, and then here's the certificate we want you to present when you make connections, right? So the server now knows how to read configuration, use certs, and the client knows how to send them. And we're gonna, again, in our loop of our client, we're gonna, every second, we're gonna connect to that target and try to get the target's names, right? Not only do they have our cert and they can use that to get our names, we have their cert and we can use that to get their names and verify who they are. Again, totally optional, but it's really cool to see that data come in. So we'll print that out and we'll print the headers and body like before. And we can't code demo yet because we don't have certs, right? Congratulations, you've written client and server code that knows how to deal with certs, but we don't have any yet. What does that say? Oh, somebody's coming in. All right, I can't read it from here, so. So let's go ahead and start with flavor one, completely manual mTLS, right? Let's start from bare bones. We're gonna issue all these certs ourselves. For this demo, I'm gonna use CFSSL. We have a lot of ways to generate certificates. You can use OpenSSL, but I find it really painful to use. I always have to look up how-tos and like snippets of those commands because they're just nightmarish. I'm glad it's there, but CFSSL is something I got familiar with when I was doing a lot of etcd setup, and etcd does mTLS between all of its members, and they use it because it's just a bunch of JSON configs you feed into either a service or a binary, and you get certs at the other end, and it's way easier to deal with. So the first thing we're going to do is generate that root authority, right? We said we don't really want to get certs from Let's Encrypt or DigiCert or whatever. We want to become our own authority. And part of that is generating that authority's certificate and key ourselves. So you'll see this a lot for CFSSL. We're going to make a directory to put our certs in. We're going to write a config file with this kind of here doc in bash, because I like putting it just all in my script and not having a lot of files here. So we're going to basically write a file with this content saying here are the hosts that the CA should be valid from. Here's our key configuration and our names. Not super interesting, but we're making a bare bones CA here. We pipe that JSON, we pass that JSON into our gen key command for CFSSL and pipe that into a CFSSL JSON command. This is a little confusing if you haven't seen it before. The left side of this is basically going to generate the certificates and output JSON, where the contents of the certificates and the key and everything are fields in a big JSON map. The right side of this pipe is another command that reads that standardized JSON structure and writes them out in a directory structure. That's all this is CFSSL is designed to be an API first. And so they have these little helper commands to generate the stuff, spit it out as JSON, and now take that JSON and use it to write files. So you'll see this a lot, but that's all it's doing. So when I run this, there we go. It made that file, it generated the CA, stuck it in my directory, and we'll see the actual files here later. But now we have a CA with which we can sign certificates. First thing we're gonna do is generate the server certificate. Same exact thing, except for we're gonna put a few more fields in here. We're gonna give a common name. Shouldn't use because it's been deprecated for 20 years, but people still use it. We're gonna set possible valid hosts. So if you contact a server that presents you this certificate and you didn't contact it at one of these 4 addresses, then the certificate's not valid, right? So they come from localhost, the local IP, localhost, server, or this fully qualified domain name. Any of those are valid. If you talk to the server with that and it gives you this cert back. We're gonna say that it's for server auth and client auth. I know that part's weird because in my demo, it's called server, but in a real microservices situation, you might be one services client and another services server. So typically these are always set for both usages. Even though we're only gonna use one of these now, I just set it for both. And this is the same key and metadata from before, I just shrunk it down to fit. Again, we're going to copy the CA that we generated. So we already generated this certificate authority certificate. We're going to copy it into our server directory to make a few commands easier later. And then the same stuff. We're going to say CFSSL generate a certificate using this CA and this CA's key, right? If you're going to issue a certificate off another one, you need its cert and its key. Just its cert isn't good enough, which is important because we're going to distribute the CA cert all over the place. But we're going to take those and then feed it our JSON config and write that to a new directory, right? So again, make a JSON, send it through some commands, get certs at the other end. I'm not going to dig deeper than that here. And the client looks almost identical, right? Here's the client's JSON. I put the word client in all the places that I used to put server. And same thing down here, I'm generating in the client folder. No big deal. So we've now generated 3 sets of certificates and keys. Let's look at those real quick. So if we cap those out, and this is all done live, this is not fake. Like those, when I hit run, it's really executing these commands. Here's our CA, where we've got our JSON, and it generated a request for us. These are the important pieces, the certificate and the key. Here's our client certificate and key. Again, we just copied the CA. It's the exact content as our PEM up here. It's just easier for minutes later to stick it in the same directory. And same thing with the server. We generated certain key. So one of Paul's original point when we started talking about this was, who owns the CA? Where do the certs live? This is the question you have to answer yourself anytime you're magically sold mTLS. So we can answer this question. Who owns the CA? We do. Where do the certs live? On our directories, right? How do we secure them? We secure those directories. This will get more and more obscure as we go. Those questions will get harder to answer, and I'll try to answer them as we do new flavors. But even though this was a pain in the butt, we understand where everything came from, right? Very obvious where the config for every value came from and where it lives. So let's now, before we go to Kubernetes, let's just run our server code. Remember, our server code takes the cert file, key file, and the CA file. So we're going to run that server and give it the paths to those 3 files. And we're going to run that in the background, wait for it to start, and run our client with the client's 3 files and where the server is going to be, right? Very much like our original execution. We're just doing it by passing it all the data it needs. We happen to generate these files ourselves, but these commands aren't going to change much as we use new methods to generate those 3 files. So here we go. Again, don't worry about the kill. Bring it up. Here comes the client, and there we go. So here's the server saying, here's some verified client names. We know that the client that connected to us while we're handling this request, we trusted, presented us a certificate that can trace down to somebody we trust. And here's the data about them. And then here's the headers they sent us. And then here's the client saying, hey, I talked to the server, and they could present me a certificate that was signed with their key that I could trace all the way down to somebody I trust. And here are their names. You don't have to get the names to have that trust be established, but it's really cool this data is in here. And you'll see, again, this get more and more interesting as we go on. Other than that, we still have the body. And like I said, here's the response body where we can use the names in the actual handling of the request now. We have extra data about you while we're processing your request. You didn't need to send me a client, like an auth header, didn't need to do a JOT issuing, like none of that. Like I know for sure you're you because you gave me your cert. And I know for a fact there are large companies out there that use client certificate authentication exclusively and don't do passwords. It's like, we don't even get to the point where you can't even start talking to our API servers until you present to us the client auth. I think actually temporal.io is one. Not to name any, like, there are a lot of companies that do it, but like there are some companies now getting all the way to that for their APIs. Like we're going to deal with client certs early. Yes.
It was also worth noting that we're talking about like a server that we're running in Go or whatnot, but this authentication scheme is also the basis of a lot of zero trust frameworks. Pretty much every MDM framework where you're using device certificates, that's to identify the device as like an individual thing tied to an account, et cetera. Like this is such a basic concept that's like existed longer than pretty much any of our careers, and it's everywhere and we just take it for granted, and that's ideal. We want to as users, but it's worth noting that it's in those places for this reason.
Sure. No, but I mean, a lot of people have never even gone this far locally. So it's maybe you have never used it, but I want to show that you can do this with a few commands and your own code pretty easily.
Well, the interesting thing follow up is we actually trust it all.
Without even knowing, yeah.
And we'll get
And they're
into,
going to show us why that may not always be a great trust.
yeah, exactly. Yeah, when we get to the very last flavor, we'll talk about what we're trusting and what we're not trusting. So in these examples, my code at the code level has certain assurances about the security of the environment. I had to write that code, and it's kind of a pain in the butt to generate these certs, but I have a lot of guarantees at the code execution level now that we're going to keep through almost all of the rest of the modes today.
And a lot of understanding and
Utility, right?
you only had to write it once.
Yes. Yeah, I'm sure there's other things that were frameworks that would just make client auth, like in your Go, Mux, or whatever, easy to use. Or so, like, and you don't have to write your own. Again, any web browser can support this kind of stuff. Or not any web server. So let's deploy our manually generated mTLS stuff into Kubernetes. I'm only going to show you the changes. The bulk of the deployment through all these modes is going to stay the same. So I'm just going to highlight the important changes we're going to make to the YAML of our deployments. So in our case, we're going to add 2 things to our server. We're going to add a volume declaration at the bottom of the pod spec that says, okay, mount some data as a volume to all the pods that execute. And I'm going to want you to call that volume TLS, and I want you to mount a secret that's going to exist in the cluster. We haven't made this yet, but I promise you it'll exist when we run this deployment. And the secret's going to be named server-TLS. And then
777 was the only mode.
that, yeah, that's what I see most. But no, it turns out, yeah, there are other modes. And we're gonna make a volume mount in our server container. So this exists at the pod level, and then our container that needs to use it, we're gonna say, well, take the data that's at TL or that's under the name TLS, which is coming from our secret, mount it at /TLS with read only. What that means is then we can go to where we declare how we start our server in the pod spec, and we can say, instead of just calling the server with no args, we're gonna say, just like we did when we ran it locally, here's where the cert's gonna live, here's where the key's gonna live, and here's where the CA is gonna live. There's a million ways you could give it these files, but I like to just use Kubernetes to stick secrets in there and read from them. And this is gonna be really common, so you'll see this a lot. Again, not too fancy, just taking data from a Kubernetes secret and telling Kubernetes, every time you make a pod with this spec, stick this secret data in there. So let's change our client as well. And again, the client looks pretty much identical here because the client is just using the same system. It's just going to get its cert, a different secret. So we say, here's the secret name is client TLS. And we have our 3 arguments here plus where the server is going to live. And I'm changing the server name to the shorter one here. That, again, our cert doesn't care whether you use localhost one or the local IP or server or the long form server. They'll all be valid for this HTTPS connection. So let's do our Kubernetes demo. Like I said, above, I'm showing you a snippet of a script. Above this, I'm going to set up a brand new cluster, build a container, stick it in, all of that good stuff still happening. You'll see it in the logs, but I'm not going to show you it anymore. What I'm going to show you is the new thing in the demo script, which is we generated the certs by hand. We still have to put them in Kubernetes so that the deployments can read them. And we're going to do that by deleting it if it's already there. I'll put that in there so I could rerun the script as much as I wanted. Otherwise, we're going to create a secret called server TLS, and we're going to just pass it this from file argument 3 times. And each time we're going to give it the path to a file. And if you've never done this, what this does is every time you have one of those args, it's going to read the content of that file and put it in the secret under a key where the key is named based on the file name. You don't have to do anything else. It just automatically says, well, if this is the file name I read it from, it's going to have this name in the secret, which makes it really helpful later because when I mount this stuff, under this directory, Kubernetes is going to make a file based on the content of every key in that secret, right? Secrets are just key value pairs. So if I make, essentially, if I create this directory following a file structure, then when I get it back, I'll get those exact file names. It makes it really easy to not have to worry about what this is going to be called when I get all the way into my code in the deployment. So essentially, we make the server TLS, do the exact same thing for the client TLS from a different directory, and that's how we get those secrets in. This is part of the problem of this mode is somebody out of band. I don't want to put this in Git. I can't GitOps these secrets because my keys are in Git. So somebody somewhere else, in this case, it's us, are going to jam those certificates in there, including if they expire, we need to regenerate them, put new ones in there. Somebody's got to go generate them and update them. So it's not super easy, but it is completely possible without almost any extra tooling to do all this ourselves. Finally, we apply our updated server and client YAML, wait for them to come up and follow the logs. So here we go. Now we're making a new K3D cluster for our manual TLS. It's going to bring up the new cluster and it's going to actually generate the certs, generate the CA, generate the certs, stick those new secrets in and create the new deployments and services that read those secrets. It shouldn't take too long. There we go, building the Go image, ripping it out to a R file. We'll see this a few times. Again, don't worry about this. I could wait longer in the demo for the metric server to be up in the K3D cluster I just made, but I don't care. Our command made that secret with all the -- file arguments, and then we made the client one here. We made our deployment and service for the server and the deployment for the client. They both came up and scroll all the way down. Hey, look at that. This is now in Kubernetes, the same exact thing we saw in our local exec demo of running our secure service, right? We still have all of the same verified client names. So this is the server saying, okay, here's the client coming in. I trust them and here are their names. The logs start to get interleaved here as we start to have more and more things going on because kubetail just interleaves lines together, but it's here. We scroll down and look for some of these left ticks. we'll see that, yep, here's the client saying, here's the server names, the server headers, and the server body. So we've done all of this. We've actually now, this is the first complete example of mTLS completely working in Kubernetes, right? This is maybe not a super shock, but this is an example that you don't need fancy tools. You don't need anything extra. You have to maybe build a bunch of automation if you wanted to scale this up, but you absolutely can do it by hand. You could script this. If you had 5 services, you could script this. You could script updating them, building new certs once a year, whatever, like rotate them as often as is convenient. Like you don't need a full service mesh to do mTLS if you don't have massive scale. Even this is sustainable at smaller scale. What is that?
Is the K service now routing on layer 4 instead of layer 7? No.
No, it is. Yeah, services are always layer 4.
Services are always layer 4.
It depends on your definition of routing, I guess.
You're hitting DNS, you're getting an IP address, and you're creating a layer 4 connection to that IP address for the Kubernetes load balancer. So.
Is it both?
And then if you're hitting a proxy, you can be routed at layer 7 at that point.
Yeah, but we're not in the proxy here. So this is completely layer 4. This is like when the client talks to the server, it's getting sent through the load balancer, but that's again all like layer 4 load balancing to a server for every connection. You're right though. When we get into the service mesh, that's if you want layer application layer, you got to use service mesh stuff or something fancier. This is keeping it way low. Like, there we go. So that's our first flavor in the books, like mTLS by hand. But that kind of sucked, right? I don't want to have to remember to rotate certificates. I don't want to have to remember to do anything. If I'm being honest, like I don't want to have to remember. So let's start to move this further off into something else's problem. And in our case, we're going to use Cert Manager. There's a lot of ways to do this. I'm really familiar with Cert Manager. So we're going to do kind of our first instance of this that is semi by hand, and you'll see what I mean by that. So when we set up our cluster, here's a snippet of our code. Above this is bringing up a new K3D cluster, injecting the image, blah, blah, blah. But next, before we use it, we're going to say, in this cluster, I need to install Cert Manager. Cert Manager is pretty easy to install. You can basically big YAML file and apply it in your cluster, and it'll bring up working Cert Manager. I'm not sure that it's production ready, but it absolutely works. Then we're going to use this kubectl command to just, because this is all scripted and going to happen when I click go, I want to make sure Cert Manager is ready before I start to use some of the things that's going to stick into my cluster. So really basic, stick Cert Manager in the cluster, wait for it to be ready. In this method, we still own the CA, right? So who owns the certs? In this case, we are going to own the CA ourselves, and we're responsible for still generating that authority. But now we're going to generate that authority and stick it into a secret. We didn't put the authority in a secret before because we didn't need it anywhere in the cluster. We kept it to ourselves. Now we're going to put it in the cluster so that Cert Manager can use it to issue certificates for us, right? So I'm not automating away the CA authority generation, but I am going to automate away everything else. So we still generate our CA as before. It may not be great defaults, but they work. Generate that, stick it into this search directory. But just like we kind of did with our client and server, we're going to create a secret called CA-TLS where we stick the CA cert and its key, right? So Cert Manager later will have access to what it needs to issue certificates for us without us having to call any commands. So then we're going to, now we've created that cluster, put Cert Manager in there, put a secret in there. We're going to create what's called a cluster issuer in Cert Manager, which is essentially a cluster level authority that other things in Cert Manager, other resources will be able to reference to say, issue me a cert from that issuer. And it's cluster wide because that makes it easy for me. Oh no. Sorry, I just went completely black over here. Okay. I ran out of battery because that wasn't on. Sorry, y'all. Give me a second to come back up. I know the presentation looks like it's good.
Take your time to pause.
Yeah, anybody have any questions while I'm rebooting my, I plugged it in, but it only works when it's on.
Yeah.
So,
So one thing that's interesting, not that people would do it, but you can have multiple cert managers in a cluster.
multiple issuers all day
And
long.
multiple issuers, and sometimes that even makes sense.
Mhm. Yeah, I'm doing one, but I probably wouldn't do one massive issuer because there's not good controls over what namespaces can use what issuers other than namespace scoping.
I'm waiting for the those scenarios.
Well, I mean, the thing is that you, like, he's been talking about who's the controller?
Yeah.
How do I localize my trust? That's really what it is. And what he was talking about is you could actually regulate that you have a more stringent or more confined area in which you have the cert manager being in that same vein, being more restricted and more, more proven as to be trusted. So it's not often that you would do it. But I've seen it like in Finservs. I think there's others, FinTech. I don't know if you've seen it.
Yeah, most of the time, once you start talking to companies that have like full-fledged security teams,
Yep.
very strict policies over how their CAs can be used.
Yep.
So even like in most CA as a service, you can say this CA can only have or issue certs for this set of domains or this set of subdomains. And so you could do something similar with Cert Manager if you had multiple cert issuers saying, here's one that has, credentials for Let's Encrypt. Here's one that only does internal, self-signed or something like that.
It's also fundamentally way harder to do all of that in like, the tools that he's showing us are great, don't get me wrong, but the moment you're entering in a world where you have a dozen CAs from different authorities that are animosity towards each other, even though they're in the same company, and they all have to they have a 5 or 10 year root CA that they never use because they are working off of a 3-month CA that CA is signing, and then they use that. Like, it just gets layers upon layers upon layers of indirection. And then anytime you ask basic questions about like, who do you trust or who owns that or whatever, now there's several layers of indirection that nobody actually knows involved, and the tools are not helping you with that because that's all just complication you just invented in the logistics. So the conversation becomes lacking in any sort of standards or jargon to even build understanding and talk about. It's a very interesting field, but this is also why GPG is not used in everybody's tools
Most places.
today. For the same reasons of this is all very inaccessible and there's a lot of layers and indirection, and then like you're just like, oh, I just want to send an email.
Well, yeah, but it's all doable, right? You're right. You have to
Yes.
set standards, and I would, most of what we're doing here, like the first one is an example of how you could do it with infrastructure for very few things, but like this will push more and more into it, like I don't have to worry about it, right? All the way up to the final one, which is I don't even know it's happening for whatever good or ill that means. So sorry for the interlude, y'all. I will check my power switches are actually on next time. Okay, all the way back. We set up a cluster. We put Cert Manager in there. We wait for it to be ready. We're going to create a new CA for this cluster because why not? And then going to stick the and certificate for that CA as a secret into our cluster and create a cluster issuer. To Paul's point, you could make 50 CAs and you could make like circles of trust and make a bunch of issues, an issuer per namespace. And trusting across multiple circles gets hard, but you can tighten this as much as you want. We own the CAs. We know where they're coming from. We control how many certs you can issue. And yeah, I think, like Greg said, you can even go down into some of these and restrict in issuers like what domains they'll issue for. I'm keeping this wide open, making a very generic issuer saying, here's the CA, just sign everything. But it'll work. And now this is a snippet out of right above our server deployment.yaml we've been looking at. This is a snippet for us making a certificate resource. So you won't see CFSSL from here on out, right? We did it once. We'll do it to set up the cluster. Everything from now on is a Kubernetes resource. And the cool part is there's no problems with secrets here because there's nothing secret in this manifest, right? To Cert Manager, issue a certificate called server using this issuer that I just created. Put the common name in there, which you can do, but you shouldn't. Put the 2 DNS names in there.
There was a question there.
Oh, I didn't miss
The next line, the duration of the cert.
Oh, yeah, and it will do the renewals. So give it the names. We say, I want you to have them only last for 90 days. And when they've only got, once they have 15 days left, start trying to renew. And there's no reason to wait till the last moment. You can kind of control how long you want them to last and then when you want them to renew. Is that another question?
No, he was just saying, sorry, you're fine, Kalapa.
Then we put our subject in there. I'm not doing all the orgs. That's fine. I'm just doing a simple one here and our key encoding. And if this looks similar, it's because Cert Manager is written in Go, and I'm sure, and CFSSL is written in Go, and they all kind of align on the same core set of configuration values. It's just one of them was a JSON file, and this is a YAML file with some extra stuff around the data. You need to still tell me the same things when you want to make a cert. Like, give me that info. I'm just putting it in Kubernetes instead. The important part is this. This secret is not the name of a secret we have to make. This is the secret where Cert Manager is going to stick everything it generates. Every time it generates a new cert, it sticks the cert and the key in this secret for us. So we can consume this, but have to put it in our repo because it'll just get created by Cert Manager as a result of this resource existing. Yes.
I know you talked about the usages before.
Mhm.
Those are just your strings. They're not magic.
They're magic strings.
They are magic
They're
strings.
magic strings for the library that
X509 certificate types. So code signing is another one you've probably heard of. You can't use this to sign code because it says it's only valid for server off and client off.
So they're in the docs, they're going. Yep. So moving on, we have, like I said, in that previous thing, we gave it, it's going to make that secret. So we don't actually have to change the volume section of our deployment spec, right? It's already set to read a secret called that from our last example. So we're gonna keep that setting. What we are gonna do is tweak the arguments. Because remember I said, when you mount a secret, all of the keys in that secret get created as files. Cert Manager likes to write out those 3 files with slightly different names than CFSSL does. And it seems like every single service that issues certificates likes to use 3 different names for these 3 files. Like there are no standards anywhere.
That is the standard though.
Is the bottom one standard?
No, there's no standard.
Oh, the standard is there are no standards. So we have to rename, these aren't gonna be called TLS.pem, TLS key, they're gonna be called TLS.cert and TLS.key. This is more like a Kubernetes standard I see in a lot of places. This is what Rick wants to use, so it's fine. Like, we just changed the name. I wish they'd standardize, but it's not that hard to tweak the file names we're looking for. Our client,
Team competing standards.
that's right. We should make a new standard.
It's worth noting that the difference there will actually limit, you'll have to do some of that translation before you use certain servers like, I don't know, Apache versus Nginx versus anything, like, they all have the kinds of formatting that they work with and the kinds that they don't.
Some of them like a CA, some of them want you to put the
Mhm.
CER
certificates.
right? So both of those I would expect to actually just be PEM. PEM is like the generic version, and CRT usually means public key, key usually means private key, but they're both usually PEM. CER is the one that Windows made, that then is some
And it's,
other format that always gets.
Because 12 versus, all the other junk.
and if we had wanted to standardize the previous one to these names, I could have renamed the files. Maybe there's some flat, like, but yeah, you're right. They're not always plug and play, so.
Yeah, I'm just saying, if anybody is ever watching this in posterity and trying to implement something and they're like, I'll try to take this further, they'll see problems, and the key infrastructure is notorious for not giving very good error on like what you're supposed to be doing because they can't figure everything you're supposed to be doing.
It's all secret stuff.
Well, no, what
Are
it
you
is.
saying you should use a service mesh? It sounds like you're saying.
No, no,
All
no.
right.
Usually with security though, it is a binary question. Does it work? Doesn't work. That's usually all you know.
Yeah, error happened. Good luck.
Yeah, not working.
So we've made our certificate, we've linked that certificate, the secret that certificate's gonna make to our deployment and pointed it at the new names. We do that with the client as well, make a client certificate. So this looks really similar, but it's got the word client in all the new places. And that's gonna write to client.tls. So same thing, we update our secret volume to point to a new secret. Or not even, we don't have to update that, that's the same. We just change our args, right? Yeah, we're getting in the weeds on names because this is what you spend half your life fighting with. You'd think the cryptography would be hard, but it's 3 file names that are hard. So we're gonna then, at the very end of all that, set up Cert Manager, generate our CA, stick it in, create the issuer, create our certificates and our deployments, and have them talk to each other. These apply the certificates, the deployments, the services, and wait for them to come up and follow them. So I should jump while we were all chit chatting because we're gonna have to watch it bring up another cluster. But that's fine. It's pretty fast. I mean, considering we're going from nothing to a fully functional cluster with cert manager and all these things made and like injecting it with our images, I don't have much of a problem with this. Most of it is just waiting for things to bootstrap. Here we go, bringing it up.
Update your terminal thing to have colors on it.
Yeah, that's Go Present. I know, it'd be a fun add-on. What I want, we were talking about this, what I want in Go Present is I want diagrams. Because all the ones I have there, I have to link generate as images and link them. I tried feebly to get Mermaid to render by overriding the templates here, and I got it, but they always looked bad because of some sort of, I don't know what happens when Mermaid renders in like this page. So this is just a web page. So we'll get there. All right, so we bootstrapped everything. We got all the way. Here's Cert Manager being installed and setting up all of the things it puts in our cluster. Here it goes, still going. All Cert Manager. We're waiting for Cert Manager to come up. Once these are done, it says they're all ready. So here's us. We made the CA. You can't see that in the log, but we made it. We made the secret for the CA. We made our issuer, our cluster issuer. Then for the server, we said make a certificate, a deployment, and a service. So this now was going to issue certs, renew them, all that good stuff. And for the client, we would say make our client certificate and our client deployment. There's never been a service for the client because nothing's talking to it, so I don't make it a Kubernetes service, but it still has a cert. And we scroll down. Here, all the pods came up and we started getting their logs, and it looks the same as the last two flavors because it is the same, right? We have data in the certificate resource for Cert Manager that says, here's the names you should trust, and we've been using the same ones. Other than when we were manual, because I was lazy, we let localhost be valid and the deploy names be valid, which is probably bad practice, but I'm lazy. So here's the client saying, here, when I talked to the server, I trusted them, here's who they are. And the server saying, hey, when I talked to the client, I trusted them, here's who they are. And again, getting all that data in the response body to say, thanks, whoever you are that I trust, here's your names. Thank you for using mTLS. So this is our third way of doing mTLS all the way done, where we've shunted more work off into Cert Manager. Answering the questions, who has the certs? Who has the CA? We do. Where do the certs come from? Cert Manager. Where do they live? Kubernetes secrets, right? It's pretty obvious because we tell it where to put the cert. We know where it's going to exist. Now, Cert Manager has gears in the middle between the certificate and the secret, but mostly we know where everything is. And if a cert's not getting created, you can basically describe objects in Kubernetes and see what fails along the way. And it's pretty obvious when things aren't working, you can kind of walk back where they're not working.
But also, this is why you secure etcd as well.
Yeah, exactly. Because now all of your client and server, everything's living in your Kubernetes secrets. So they're still in there, which is just how it works. Now let's go ahead and move on to the next one. So layer 3, we're going to still use Cert Manager, but this is the whole reason I want to do this talk, because I wanted to mess with CSI. Do not be confused by the S. That is container storage interface, not secret, although I think there's a different competing standard for secrets. So essentially, we're using Cert Manager to issue certificates, and it's going to just mount them straight to volumes for us, which is pretty cool. And you're going to see it gets even more detailed. So above this snippet, set up the cluster, inject the image, blah, blah, blah. But now we're not just going to put Cert Manager in. Now we need to install Cert Manager the normal way. So this is the same way we did it before. Get a big YAML file, jam it in the cluster. Then we're going to wait for it to come up. And we're going to use Helm because this is the way they want you to get this. We're going to add our JetStack repo. We're going to, in the Cert Manager namespace, upgrade, and the -i says, if it's not there, stick it in there. This is just their best practice. I know it won't be there, but whatever. I want you to, in the Cert Manager namespace, install this Cert Manager CSI driver Helm chart, which is essentially just a webhook. This Helm chart sticks a webhook in your Kubernetes cluster and tells Kubernetes, hey, when people try to create a volume with this driver, talk to this service to get the contents of that volume. Right? Before we were saying, we're going to mount a volume from a Kubernetes secret. Now we're saying, it's not going to even be in Kubernetes secrets. Just go talk to this thing and it's going to give you a cert back. And then you stick that data in your pod. So we're taking the etcd thing out of the equation because these certs will no longer even live as secrets in Kubernetes. But you have to, in order to do that, you stick Cert Manager on there and then stick the CSI driver in there. On a fresh cluster, it's going to work. The other big thing, when you move to Cert Manager with CSI, self-signed CA isn't going to work anymore, my friends. They just straight up say, you can no longer own the authority. You need to have some better PKI system that's going to issue these certs. We won't do, we won't do self-sign, which is what when we made our own CA, and said use this CA to sign things, they're calling that self-sign, which isn't exactly right, but that's what they're calling. So I'm gonna use Vault. They don't care how you do it. There's a bunch of different PKI systems that Cert Manager will integrate with. They specifically point you at the cloud services that will do this, where for a pretty cheap fee, they'll be your CA and issue your certs for you. But because I want to run this locally and not need any dependencies, I'm going to add the HashiCorp Helm repo. I'm going to create a Vault namespace, and I'm going to install Vault in there in a really bad, insecure way, but it makes demos easy. I'm going to say it's a dev mode, and here's the root token right there in plain text. I don't really care. Dev mode means everything you do in Vault will be gone as soon as you delete that process and start it again, because it's all in memory. And then the token is like, here it is. You can do whatever you want in this Vault. Really insecure, but again, you set up Vault however you want to set it up in your cluster, and then you use it. Yes.
So with the CSI stuff, is it, so if it's not in etcd, does it exist in memory, like a temporary file system, or under the hood, what's CSI doing?
It exists wherever the webhook gets it from. So when you go to mount that volume, and we'll see it in a second, and it talks to the webhook could be getting from database, could still be getting it from etcd or Kubernetes. Like, it's just the rest of Kubernetes resources don't play in. It's just the response.
Look at the actual driver itself.
Yeah, they sometimes call it projected volume too. So like, it's probably still in memory on the node because it has to be.
Okay. So that's what's happening.
Or the same place that the container image was extracted and like turned into a virtual or the squash file system.
Yeah,
But
so
it doesn't have to be persisted in etcd just to get it into a container, which is a required path for a secret.
So yeah, like a lot of things, if you had root admin on like the Kubernetes nodes, you could probably dig in and still find this data somewhere. But
The README for it says that it ensures private keys never leave the node and are never sent over the network.
It also means that if you are writing your own Kubernetes distro and you want to shove that in a TPM, you probably can. So it could be backed by something as secure as a TPM if you do the legwork to make it do so. By default, it's probably not, but.
This is specifically designed to be able to enable the enterprise nonsense that requires, acts of Congress to spin up a new server or whatever. So whatever flavor that is, and there's hundreds of thousands, that's what this is for, is to be able to be that flexible and enable those guarantees.
But CSI could also be for totally non-secret data, right? You could totally have a CSI driver that just sticks like time in, or whatever. Like it could be as fancy as you want.
Yeah, use a Canon as a digger as well.
You can, absolutely. Honestly, I'm just saying, like, pointing out how secure it can be, which is really cool, but it's fundamentally the tool is just there to be a volume interface. So we install Vault with Helm. We wait for it to be ready because we're going to do some things with Vault, and I've got notices about here. I might not, unless you already had Vault, I would probably try to use a cloud service that you're in. Although if you've already got a big Vault installation, this isn't a big deal. I need to prep Vault now. So I've got a basic Vault in insecure mode where I've got a root token. I'm going to port forward to that Vault instance, wait for that to establish, get the address, set up some basically environment variables so my Vault CLI can talk to that instance, right? I'm basically tunneling into my container, setting up the token. Then specifically say Vault enable the PKI module. And I want to tweak how long I want my cert to live, because I have to actually not only have to say Vault turn on PKI. I'm not generating the CA. I don't have the key ever directly, but I do have to tell Vault now make the CA, which happens here. So I say Vault write a certificate to this root and generate the root certificate with this common name, with this issuer name, and I'm going to write it out. The cert, not the key. In this case, I don't own the key. Vault owns the key, but it does give me the cert, so I'll need that later. I'm also going to make a role in Vault that I can use that allows you to basically issue, it's going to let Cert Manager issue for any name that I want. Then we set up our cluster issuer. In order to do that, we need to make our secret. We're going to actually tell Cert Manager, this secret is not the CA anymore, right? The CA's key we never got. We just got its cert, and that's not really secret. But we do need to tell Cert Manager, talk to Vault to do all this work. And in order for us to do this with the token, which again is not the optimal way to connect Cert Manager to Vault, but our dev way is stick a token in there so they can talk to Vault with that token. Then we make our issuer, called the Vault issuer. here's that signer that we made that can issue for any name, right? So again, you could lock it down and restrict names, blah, blah, blah. Here's where Vault's gonna live in my cluster. Up here, I'm taking the CA bundle for that root cert and saying, this is the bundle I want you to attach to all the certs you issue. This can get way more complex than that root CA. In fact, most good PKI says, don't issue things with your root, issue intermediaries, and then, right? Because you have a whole trust chain. You don't have to issue with that. I can issue a couple intermediaries that I trust to do all the work. That way, if something leaks, I just have to cancel those, not the entire like family tree of my certs. But we're base 64 encoding that, so we can put in our issuer and then telling it, hey, when you talk to Vault, here's how you get the not the best way, but set up Vault, set up PKI, and then tell Cert Manager how to talk to Vault so that we can issue things off of Vault. And this could be in combination with our self-sign. This could be in combination with cloud providers. Like Cert Manager is there to just orchestrate issuing of certs with all these different systems. You're often just plugging it into something else to do the hard work. Notably, in both our server and our client YAMLs, we don't make a certificate anymore. That certificate resource you saw where I put in all the methods and renewals, and that's gone. I don't make a cert anymore. And I didn't even make a CA really. I kind of just told Vault to make a CA and then told Cert Manager where to find it. So we just take all this out of our server. And instead, in this volume where we used to just have secret name, whatever, remember that was what we did up to now. Now we use this CSI extension. I want you to use a CSI module. I'm going to still set it to read only. Here's where I tell it what the driver that I installed was, right? This is all part of that Helm install. And I can use attributes, which are basically just annotations to say, use a cluster issuer called Vault Issuer for this thing. So I don't have to use that one issuer if I want for every single deploy if I didn't want to, but I am. And I'm going to set up DNS names in here, and I'm getting real fancy. With my YAML, using these run-on inline strings that totally work as valid YAML. This is the exact YAML I'm using in case you've never seen this just run over like this. It totally works. I'm going to say the DNS names for this should be server, and the namespace of the pod. So I can kind of, if you know anything about Kubernetes DNS access, when I go to a service, I can go to by the service name qualified with the namespace, or the fully qualified one. All of those are. Before I was only doing 2 of those, so I might have had issues. Now I'm going to iterate all of those, and I don't even have to know the namespace. Like you'll know that based on where you're putting this pod with these placeholders. And this is my favorite one. So all 4 of these comma separated values are going to be in my server names, and this one is down to the pod name, because even if I don't use use the DNS names and make this hyper specific, every single pod that is created is issued a unique certificate for that pod and that pod only, down to that pod. Again, I'm sticking the name in here to be really cool, but whether or not you stick the name in here, every pod gets a unique cert. So if a cert gets leaked, guess what? There's only one cert impacted. There's only one server, not even one service, one pod impacted. Really cool. And again, Combinate's been deprecated since the year 2000 for a bunch of reasons, not least of which is it's a really restrictive length limit, but you could set that in here if you wanted to as well. I really recommend get on the DNS names train. The client volumes, same stuff. Get rid of the certificate resource entirely from my YAML file. Tweak the volume. I've condensed it. These are the same attributes as before. I'm just squishing them up so I can fit them on one page. Right? Use Vault. Names are client dot whatever, all the way down to the pod name and pod namespace. So you know for sure who you're talking to, whether you access them, all the different levels of abstraction, including going directly to that pod by its exact name and namespace. So
You just kind of have to know
there's docs on.
what Vault is injecting for names and.
This is Cert Manager's rule. So like you'll know what in here, what things you can put between the
But as
brackets.
far as like identifying the name and the stuff that you were manually setting before.
Sorry, which stuff?
I don't know.
Files? Is that what you're talking about?
The files are actually going to be the exact
What
same.
about the data inside the cert? Like you were choosing an organization and.
Oh,
all
that,
Stuff.
you got all that here. I'm just not doing it.
Okay.
So if you want to tweak all the other name attributes and stuff, that's all in there. Essentially 100% of data about the certificate that you're going to put in here goes into the pod spec. That's all still, I don't set it. I probably should have, just to be consistent. But yeah, that's the fun part. Is like, it's all just in the pod spec now. Like everything else doesn't matter. Including This is Vault. I'm calling it Vault Issuer. If I just called this Issuer and somebody administratively was changing it and didn't use Vault, whatever, like it's still, to me, it all translates to the same set of root trusted CAs. Like I could swap issuers out. Like it doesn't have to be Vault. Cert Manager says just give me an issuer and I'll issue you certs.
Cert manager also isn't speaking like vault specific protocol or anything. Like it's just talking PKI standard. here is a cert, please sign it. Kind of thing.
Please. So that was all. I've showed you pieces of Kubernetes demo as we've gone. I didn't show you the cluster setup, but that's all of that. So that's all going to happen. At the end of the day, we just apply our stuff. Important to note, every time I show you new cluster setup, that happens once when you install the cluster. Like I'm going through how we get these clusters going. You just do that once and it's done, right? So here we go. We're going to let this go. I should have let this go while I was talking. And Cert Manager is not the only thing that does this. I just, like I said, I'm picking 5 flavors and we're doing 5 methods because I like just building and building. Because we already use Cert Manager for our normal server certs, right, that we're getting from Let's Encrypt. And it's cool that you can extend it all the way down to something like this that use like per pod certs.
It's also,
Go ahead. Say, how much overhead is there for creating the cert? Right, you've got auto scaling servers and clients and.
Are you stack me? Exact same.
I mean,
Well, that's just free.
Longer because they require stable. So like they require that a DNS record is stable so that somebody could have just injected the packet at the perfect moment of time.
So I can't see if pods slow down.
It is a CPU cost. I mean, it's
Way less than the TLS that'll happen on every connection.
crypto, but it's not.
Well, I'm just curious, like, I mean, is it milliseconds, so it's imperceptible in terms of pod startup?
We'll
single digit milliseconds on any modern network.
If you're using like a PKI as a service, getting your request to that instance is probably going to dominate the time. It actually doing the signing, they're all usually designed to scale up. Same with Vault, like Vault.
we'll scale our clients up and see when we're done here. 'Cause it-
Vault would probably last for your first 50,000 pods pretty easily if you give it just a reasonable amount of resources. Like you could churn through a pretty good amount of workload and Vault hold up to that for this. If you're also issuing other certs and then like you probably wouldn't want your pods to be created and die within 5 seconds. If you're having to get new certs every single time, it may start consuming more resources than is worth in that kind of environment. And you might want to find a way of doing caching or something, which some of these can provide, some of them can't. Like you might switch to a stable set so that you at least get the same pod name so that if it did have a cert, it could reuse that issued cert.
So we bootstrapped the cluster, built my sample code, jammed it in there, installed Cert Manager, waited for it to come up. Here's where we use Helm to install the CSI driver. And then we use Helm to install Vault. We scroll all the way down. Here's where we set up our port forward to Vault. This is where we turned on PKI and tuned it. We wrote our signer. Again, this is all the steps I showed you, just the logs of the results. We created our Vault token to set a Cert Manager up to talk to Vault. Then we create our issuer, and once that's done, we make as many services as we want with those Vault, with those CSI annotations in the volumes. I'm doing 2, do 50, you do whatever you want, it'll issue them. So we make the test server. Again, there's no cert here anymore. There's nothing else but the deployment. The deployment has enough to trust the cluster to do a lot of this. Scrolling down, this is where it gets really fun. Certificate names, if I scroll, so this is from a client, right? Saying, when I talked to the server, it was somebody I trusted, and I could verify who it was, and guess what? I can tell you exactly what server I talked to, because it's in the names, right? Like, and the same thing with the server. If I go to a server response saying, hey, I talked to a client, I could verify them all the way, somebody I trusted, here's their names. I'm handling a request for this client. So I've now done essentially free, along with security, trust, blah, blah, blah. I've got free all the way down to the pod level verification and identity, right? Available to my code. My code can now make decisions. I don't know what you need to do on the pod level, but it can theoretically make decisions on this data and use that identity as far down as it goes. You can put in logs, it can do all that cool stuff directly. It doesn't need anything else. It knows I'm handling a request for that thing over there right now. Really cool. So, and let's do that to scale it up. I'm curious, Derek asks, so kubectl git o. Scale. So this is, again, remember when I ran the K3D, it set up my local kubectl to point to that cluster directly. So I'm automatically working with that cluster we're viewing on the other page. Scale deployment, test client, replicas, 5. And container creating, and it's up. So imperceptibly, and a bit, no time at all, like no time at all to do that. Way faster actually than using certificate resources and waiting for those to create secrets to mount in your pods, like, well, other than scaling up, yeah, pretty fast.
You're no longer having etcd replicate for you.
Yeah, exactly. Well, and again, certs live only on those nodes because that's how CSI works. Is I actually didn't know that, so we just learned that like those only live on those nodes. So
That's the other thing that's nice about the projection is I think it'll wait for it to exist, whereas if you reference a secret that doesn't exist, you can get into like a back off pretty quick versus,
yeah,
that's why they switched to the same thing for tokens is you no longer have to be worried about, does the token exist at the time that the pod starts? It will actually stall the pod knowing that it's waiting on a resource that is still in like provisioning status.
Rather than like a crash loop back off.
pretty cool. So that was it. That was our last version. This is our last demo of our own. Yes.
Before you move on, this is the last, well, this is probably the only flavor actually that you can use with not Kubernetes at the same time. Like if you have other infrastructure that you need to have like a CA, PKI stuff for, this is the last point that you can do an mTLS without like a whole lot of hoop jumping to get like those certificates issued for like some VM or something that you're gonna share the same CA and all that signing authority chain, et cetera. Everything else before has been Kubernetes centric and Kubernetes only without some hoop jumping. And when you move on, it will also be Kubernetes centric purely.
Well, I argue that completely by hand is not Kubernetes centric. You can put files anywhere, any way you want. It's just a pain in the butt.
Yeah, I just consider that like not.
That's not
at
feasible.
all. So
Fair enough. Yeah.
Why not?
So question on
it's not.
CA, root CA versus intermediaries. Right, so I'm pulling up Google Cloud certificate service. It's like 30 cents a cert, where it's like, well, I don't want to pay 30 cents every time a pod starts up. And
There's two SKUs. There's a enterprise and a DevOps.
yeah, that's the DevOps is 30 cents.
Percent. Sure.
Cert,
Is that for
first 50.
thirds?
Oh, yeah, for the first 50,000. So at scale.
At scale, it goes down to 0.0009.
Which I hope that you have that problem, right? Scaled it.
So
So
you're
can
asking
you like say, hey, this is my root cert, and then the Kate's API server or cert manager is an intermediary, so you're not paying.
So the charge would be per leaf, unless you're saying per certificate pool. Is that what you're saying?
It says 30 cents per certificate.
Yeah, so that's the leaf. That's the thing you're generating. And if you're doing mTLS with shared certs, you might as well not be mTLS. So it would always have to be per endpoint is how you usually set up PKI.
like this is, yeah, you're right. It might, and you can.
So I'm saying if I want to not pay Google to sign everyone.
Then you use Vault.
Basically, that's how Cert Manager wants you. Use a API provider that it integrates with that's not self-signed.
That would have been 30 cents per service, not per pod, is what you're saying, right?
No, per pod.
Every
Just
you
per-
get a new cert for
Per
every pod.
issued certificate.
In this scenario, for the MTLS, it would be per pod.
And I don't want to get to 20,000 a month on cert.
So
Well, even if you
it's
don't.
why the default CA for service mesh doesn't charge that. It rolls it up into the endpoint pricing. So they use mesh CA instead. But mesh CA doesn't have all the requirements of the full CAS. And basically what it says is if you want all of those features, it is going to cost you likely at least 5 figures, if not 6.
So what's the point of an intermediary if it can't
Blast radius.
sign stuff?
You
So
can't.
I can't.
You still have to set up the trust,
Yeah.
right? You could have yours be an enemy. Well, you can't, but yeah.
And the right way to think about it is, so just like he never saw the private key, that's what you want. So you will generate a private key in one place at the root. That usually doesn't exist on any computer. That is going to be on a physical, like encrypted device that you send to a vault in a bank that requires keys to get into, right? Because if you lose that, you lost everything. And if it's a public CA, you have to go hope that all the browsers will let you get back into their club because you've now shown that you should not be trusted and they may not let you back in the club. So that's why you should never use your most secure asset, which is the root, for trivial things like actually signing the certificates. And then the next thing is usually to scale it out, because you're doing that multiple places, you might have it that you have 5 different regions where your CA is available, and each different region has their own intermediate. And then that way you can know, oh, well, this was signed by that region. Or you might have business units, or you might have, name it XYZ. And oftentimes, if you have a really good security team, they will at some point be willing to give you an intermediate. They will never give you a root, right? Because if they give you an intermediate, they can own the chain, make sure that's secure. They can put policies around your intermediate saying, this is really only good for tests. So test.weave.com, that's all you can use this for. Have at it. We don't care. You can't fake google.com with this. We feel secure giving you access to this.
So like, I say, I don't want my little self-hosted vault to be the root. So Google, here, issue me a cert or one cert for 3 vault regions. And then those do that.
If you're using Vault, you could do that. They actually, I think they have a issuer that is SSLC or CFC, CLS,
Probably.
whatever. They have an issuer that you could use that's very similar to his first one. And you could just get it an intermediate. So it still needs something like injected into it, but you would just inject the intermediate into it and then let CAS sign it. And so once you have an intermediate, you can sign as many things as you want. You create as many certs as you want with it.
That's my point, is I'm trying to not pay Google money.
If
I was
you
doing
don't want
this-
to pay Google money, you set up Vault.
If I was doing this production wise, I would make a root CA by hand, out of band, generate an intermediary for each cluster that when I kickstart Vault, instead of saying, make me a root CA, I'm gonna say, like, I'm gonna issue you a certificate to sign with. It's still doing all the same thing. It's still, you create a signer and Vault says, sign these certs, but it's not signing with the root. The root I made once, locked up somewhere, and made a new one for each cluster so that if something happens with the cluster CA, I have a reduced blast radius, right? So, but you still have to use Vault. Like, you can't both leverage somebody else's trust while also doing your own issuing, just without, again, still, you'd have to put your CA in the chain no matter what.
And by the time you don't want to pay Google to do it, you might as well just set up Vault and own it end to end so that you don't want it at all.
For to store my roots, certs in LastPass.
I also like in the URL.
So does the NSA.
But it's a more serious question. So like in your test con and test server, like there's a lot of application code that's very PKI aware. I think what's selling points of service mesh is that all of that's done transparently, like applications don't need code changes. So like what are the pros and cons of doing it this way?
We'll get into that. So
Okay.
that's the very last flavor. We've done 4 out of the 5. So the very last one is that. A lot of application code. I had to be aware. I had to generate certs. I want somebody else to do it all and for everything to just be without me knowing about it. So let's do that. We're going to install the Linkerd CLI. I'm choosing Linkerd because it's the easiest one to get going, the most lightweight. So we're picking all service mesh. Linkerd, install CLI, make sure it can go in the cluster, install the CRDs, and install Linkerd itself. Just literally the get started page from Linkerd here. Wait for it to come up. Once Linkerd is in my cluster, well, what about code changes? Well, the whole point is the code, you don't change it, right? So what we're actually going to do, what we're going to deploy in the Linkerd cluster that we're making is our original insecure code. The code no longer cares. The code says, whatever, I'm over HTTP, there's no TLS involved, I don't know who I'm talking to, and they don't know who they're talking to. I assume somebody else is solving that for me, right? Which is the selling point, because this is simpler code. Undeniably, this is simpler code to understand and to work around. Our client code reverts. This is the original client code from the very first version, the insecure. I'm going to use these when my Linkerd install because there's nothing stopping me from doing both. I could use Linkerd to do free TLS, mTLS at the top and do my own mTLS down here. And there might be reasons if you really, really wanted identity for like client auth. But generally speaking, the selling point of these meshes is get MTLS from us because it's easier because you don't have to change your code. Or if you can't change your code, that might be a huge reason to use a service mesh. So we're gonna actually also revert our deployments. We're gonna take all the volume stuff out, all the cert stuff out, everything. We're not even gonna bother. We're just gonna go in here and in our server, we're gonna call the server, new arguments, gonna call the client, just tell it where the server is. Again, we trust somebody else is making things secure for us somewhere along the line. Now, how does Linkerd get set up for our services? We have to, there's a lot of ways, but the way they have us do it is use Linkerd inject on a YAML file. It's going to search through that YAML file, find all the pods, and inject a sidecar container that for Linkerd where it's going to do all the mTLS and all this magic for us, right? So you put this control plane layer at the top, and then you go through and say, when you run your things, use a tool somehow to inject these sidecars, and then we're going to proxy everything magically through Linkerd. So we'll do that for the server and the client, wait for them to come up, and again, follow the logs. It'll be a little bit faster.
So like Rob said, yeah, they also have a mutating webhook. So you can add annotations and yeah, it'll do a lot of that stuff for you.
Yeah, there's like the injector is just like the bare bones minimal way to get started, right? Which is what I'm going with. There's a bunch of ways. I don't think the injector is what they want you to do most of the time. But this allows me to not like set any labels on namespaces. So starting a cluster, building my container, jam the container in. Once that's done, I'm going to set up Linkerd, which is actually pretty lightweight compared to most other service meshes. So here's us installing CLI, verifying it can go in our cluster, actually installing Linkerd. Here we go. Here's all the things Linkerd does. I'm not going to break these down. This is its baseline footprint of what it needs out of Kubernetes. We're waiting for it to come up, right? So the service mesh is now installed in the cluster. That's brand new. And we're just waiting for it to bootstrap. And once it bootstraps, we're going to use the tool to say, here's my YAML files. I'm not going to change them. This binary is going to read that YAML file and change it for me because I don't even want to understand what it's doing. I just want to let Linkerd like put something new in my CI/CD pipeline and assume security. So here's one of the Linkerd pods coming up. Gonna wait on the others. Second, there's a bit more to a Linkerd even than cert manager or whatever. There's a whole control mesh control plane and monitoring and logs and like.
Still, it feels about 30 pages less than Istio.
I remember my Istio list of things. All right, so here's where it found test server and then sent that to kubectl. And again, I didn't change my deployments. I said, here's my deployments, unmodified. You change them for me, Linkerd. I don't do whatever you have to do, make it work. They're up, and we're going to start our logs. And ignore the color garbage. One day I'll have more time for working on Go Present, but here we go. So here is our original server code. Remember, we don't have any mTLS data. The server doesn't know for sure at the code level that security has happened. It doesn't have any identity about the clouds. I can no longer show you lines where the server says, here is the client I am currently serving. Here's the exact, all the way down to the pod name. Like, I don't know. I'm talking to whoever could connect to me. Someone above me is looking out for me and making sure that there's encryption happening, that there's mTLS happening, and that there's identity happening. As to how I get that identity, I don't know. Who owns the certs? I don't know. Where do they go? If the certs don't get issued, I don't know. Like, that's the trade-off, my friends. Like, what do you give? You're losing. You're saying, cool, it's really easy to deploy this now. I just stick one thing in the cluster, run my YAML files through a preprocessor, or do whatever I do to inject those. But if I applied those files to a cluster that didn't support, like, I don't know for sure that security is happening, and I definitely don't have access to any of the identity stuff. Like, it's really nice because all that's magic, and you get all these other service mesh features, which I'm not going to deny are really cool. But you trade off, like, it's all done above your head. There are no assurances for you anymore. There's nothing you can do at the code level. Like, I can't 100% tell you when you're executing a piece of my code that you're secure when you got there. It's like, well, where are you running? Was Linkerd installed at the time? Did they run it through Linkerd inject before they did kubectl apply? Like, here's the series of questions that you have to tell me before I can tell you this code is executing in a secure way. Like, maybe that's fine. And if you just want encryption, this is absolutely undeniably the fastest way. It's the least setup that we've had so far, but you're pushing all that off into somebody else and you're losing every bit of extra value that's added on by having a whole mTLS ecosystem set up. And that's it. So we've done, if that's not enough, maybe next time I'll do 10, but there's 5 different ways going from.
Is that a zero-based array?
Well, because, it actually made sense for 0 to be no TLS. Like, I'm normally not that nerdy.
No mTLS.
Yeah, but it's literally 0 mTLS. So, yeah, that's why we.
But what I really liked, one is amazing. But the interesting things is that there's not a right answer.
I'm not here.
That's what's frustrating for some people, but that is the reality. And it's always a give and a take. You're getting something and then you're not getting, but it is that fine line of wanting to really know what's going on. And then there's that other one of just, let the world be good. It's all working for me. It does seem to me how I like to think of things. I like to know what's going on. And so it would be frustrating for me to look at a piece of code and go like, wait, you're not over HPS, or you're not secure?
So, yeah, we are. The cluster's doing it.
Yeah, but so there's that notion of how do you feel? What's your comfort level?
And if you want a bunch of things if you just want encryption and you want somebody else to handle it and you want all the other features, like there's nothing wrong, but it's not the only way, right? So for the last 5 years, service administrators say, you need us for mTLS because you can't do it without us.
Well, yeah, but if it goes bad, a mesh, it goes bad.
Yes.
It's like you're gone.
Yeah, correct.
TLS just goes bad. PKIs, there's horrific versions of all of those too. Like,
Yeah, that's true.
But you're lost. At least with your own, you have.
Yeah, you
Insight
know where to go to maybe cover something.
So one thing I can probably share is a very interesting approach that I took somehow, happened to several months ago probably. So probably that's gonna between flavor 3 and 4. So some cases we don't want to stick to certain service mesh yet because of a lot of variety, and still we are worried about potentially sticking forever to whatever first choice of service mesh or something. And also we don't want to ask a user to customize their YAML file or something like that. So just like a CSI, So one thing I just tried to do was make some watcher agent on the Kubernetes cluster itself to watching over the event of the service creation and automatically create such manager certificate for them with whatever static set of DNS name or some stuff, so that developer don't have to worry about customizing their YAML file error, but our agent can create for them automatically certificate stuff, and still we can achieve that mTLS without running service mesh. So I just realized that while watching over your amazing storyline, and what we did was a little bit kind of in the middle of some different flavors.
Yeah. No, that's a cool way to do it. It's, again, you're like, you're still gonna know this, but we're gonna automate at the infrastructure level, making these certs for you just in a different way that makes sense to you. All right. That's way cool. No, I like that. Yeah.
So I'm very dumb about the network. I'll just say that up front.
You always say that.
I just want it to work.
Yeah.
Most of the overhead is in the initial handshake. So you're using gRPC or anything that multiplexes connections. It's almost zero overhead because everything's hardware encrypted. I feel like I've seen that.
So there's still per byte stream overhead, like processing encrypted takes more resources than processing plain text, but establishing the connection usually goes to 0 if you are using multiplex or pipelining or stream, any of the normal, like I'll do more than one thing in this call, would make that initial upfront.
Right, we're gRPC everywhere. It's just multiplexing across that. I just feel like I saw a tweet or something somewhere that the overhead was like, 0.1% or something. Tiny on the.
There's so many variables that go into it, but it's worth knowing that, like, the sentiment you're expressing actually was a real problem until about 2006, 2008, somewhere in there. Like, I remember using a big IP F5 load balancer, which did hardware encryption on HTTPS in band. And the thing was like $18,000 per 1U rack mounted load balancer, and you needed to, if you took yourself seriously, blah, blah, blah. Like all the things there, and then like in x86 and ARM and everything else, that we just have AES instruction sets. So the only overhead's that initial negotiation, because we're talking about like 1096-bit keys, and it drops that very, very quickly. It negotiates a per connection AES key to do the actual communication over, and it's not necessarily AES, I'm simplifying, but that's all done in hardware. In stream, it's just nothing. It is nothing. It's a single extra instruction.
Right, that was my basic understanding.
It is still measurable. And if you cared more about performance than you did security, you would see gains by switching even from gRPC to like non-TLS gRPC. You would actually have more bytes pushed through your servers. But almost in every single circumstance, the overhead is so small that people just say, I would rather make sure that it's not being intercepted by the NSA or not being, having
Well, it already
things
is.
happen. And even just like, so it's a way of doing like checksumming. So like solar flares can screw up your TLS stream. They can't screw up the request going to your backend if it was over TLS, unless it hit inside the right part of the computer, right? Like it kind of makes sure that if something goes wrong, it goes wrong in a different way.
Yeah.
This is actually where my frustration with a lot of the discussion around mTLS, service mesh, all these things is probably the same thing you were alluding to at the end of there, actually. The things that make us engineers versus just programmers is the understanding of trade-offs and the realities of what we're giving up, what versus what we're gaining, and what that means to the outcomes of the project we're on. This doesn't enter into the vernacular enough. This is not a discussion point, because what you're really negotiating is not about like, well, it's convenient. Get out. When things go south, because they inevitably always do, what can you do? If things go south in a service mesh, if you don't have a way to back up and restore that entire PKI infrastructure, meaning you have to be able to understand it to the point that you can do that, you've lost. You're just waiting to lose. You're sitting around waiting to just die as a company. And that's not something that we talk about enough in these negotiations and these discussions of trade-offs. At least with Vault, there's like well-known like backups. This is how it all works. It's all open source. Like this is understood. Service mesh.
Files, when you had backup files, when
Yeah.
in Kubernetes, you had a backup Kubernetes resource.
Exactly. Service mesh, same thing. Like it's all open source. You can do that, but did you? Or did you just install the easiest one and just run with it? Did you do all the due diligence of like backing up? Did you do all the due diligence of making your CAs secure? Are you using a secure random provider? Like all things, there's trade-offs at every single one of those layers, and we're just like papering over them as an industry.
I think we probably have a lot to talk to do.
Casey had one more, but we might want to stop. at least-
Yeah, so before we stop the recording, I'm gonna say, this is a link to all of this. This is all done with Go Present. So if you pull down this repo, all the scripts are there verbatim. You can pull up these slides by downloading the repo and running the run script in there that basically does all the work to allow you to click run and have those scripting exec on your machine, because Go Present doesn't want to let you do that by default. So if you want to do any of this, the YAML files, the scripts I use for setup, all that's in these repos. It's all open, so.
He's saying the URL is incorrect on this slide.
Is it?
His most recent repo.
On the slide, it doesn't say talk dash.
Oh, did I? Okay.
Yeah, Rob, you get
You.
a free pizza. Oh, you're not here.
Offer rescinded.
You're right. I started prefixing all of my repos with talk dash, and you just have to put that in here manually.
Anyways, thank you very much. And I know
There you
you.
go. We'll keep talking, but we'll let the recording stop.
Yeah, my question